Так, доброе утро. Ну что, давайте тогда начинать.
Morning. I think we can start our session. This is the second day of the conference, and our first presenter is Kirill Borovikov. He will speak about analyzing plans in Postgres. Good morning. I'm happy to see everyone. As it was mentioned, my name is Kirill Borovikov. I represent Tenza company. Tenza is a large holding responsible for the development of a conglomerate of products devoted to one goal, that is business management. So everything that your business and your company has ever encountered, we try to automate it and generalize that, starting from some hardcore things, project management and encrypted document flow, up to some hipster issues such as corporate and social networks, as well as messengers and video connection. For all of this to live and develop, and there are more than 100 internal projects. We have 10 development centers in the country, and more than 1,000 developers work there. We have used Postgres for more than 12 years, and we have accumulated a lot of data and a lot of expertise. But this expertise is localized. So if you work a lot with Postgres, you can answer a lot of questions. But if you are a common developer, you can have some problems, like something is slow, for example, and why is it slow? And normally there are three answers to this question. So either the query was written in a wrong way, for example, you wrote it through joins or through commas, and you included 10 tables into a query. So you hope that this base is a very smart product of developers, and it will do something by itself that you don't really need to specify anything, and this is a bad pattern. Normally you have to rewrite the query. The second problem is irrelevant statistics. For example, you took this database from the dump, you didn't analyze it, the base doesn't know anything, nothing is known. So when you came there, you do not actually know whether the key is present or not. And the third issue is problem with hardware. So if you use weak hardware, you will have problems with the capacities of memory, the hard drive, or something else. And for us to understand which of these options is present here, we need to have a plan, the plan of a query. For Postgres, plan is text representation of a tree where every node is one operation. So we extract the data, we connect them, we look for them by an index, for example, and each of these elements is a node. And when the executor executes this plan, they follow this tree. Sometimes they can parallel some operations, and after that they took the responses of the data from top to bottom. And this is the way it looks like in logs. This is green on black. So it seems to us that all the figures are present and that the base has told us everything. But the problem is that when there are a lot of figures, a human cannot really understand them, especially if this is a very long text. And it is really difficult to perceive this text with your eyes, but there is another problem as well. When we can see this tree, we should take into account some problems. What are these problems about? In every node, there is the sum of the resources of the subtree that is represented under it. So, if you read some data, this data goes up. It is considered on the upper nodes. If you spend some time for data processing, this data will be shown as well. The second problem is that the time of atomic execution of a node should be multiplied by the number of cycles on this node. So when you can see that one node was executed within 1 millisecond, that is good. But if you can see that loops are 10,000, it means that you need to multiply these figures. So, speaking about these computations, it's really hard to perceive Which chain is the weakest one? Even official documents state that understanding a plan is a real art. You need to be experienced to do that. And for all developers, it's not possible to integrate it into the brain of all the developers. So we realized that we need to devise a tool that will help us do it very fast. So 2 years ago, I was actually speaking about this instrument. This is a mega tool that can monitor logs from several hundreds and even more than thousands of servers. It monitors these logs, summarizes them, and tries to display them. And, at that conference, someone criticized me. They said that this service is not a public one. Indeed, this is our internal product, and I just told you about the products that can be used in statistic analysis. And after that, I thought, well, indeed, we use the help of the community. So it was, as it was mentioned yesterday, we can also contribute to this community. So we decided to take part of this service, to start eating the elephant by parts and make a public service. And first of all, it is devised for a visible visualization of plans so that the developer could take any plan from the log, put it there and see where the problem is and what can be done about it and how it correlates with the query. So let's speak about visibility. What do we mean by visibility? Let's return to the example of the plan that we saw. This is green on black. This is original. So if we put it in this service, we will see that part of the attributes of every node go apart. So this long list of tests actually became more horizontal. The amount of our own time for the node execution, the tree node execution, the number of repeats. All of this was divided. Still, we have a lot of text here. We can make it even shorter, and here we can see only the tree that has the name of these nodes present in this plan, because we had actually put these figures apart. We can see them already. In that case, we will have more space. More space for what? To generate a pie chart. Let's look at this plan. Here we can see that we had counted the data once from one physical table, but actually 60% of time was spent to reread them when they were extracted. CTE and reading from CTE is not cheap. And this can be quite astonishing to you. So when you read it from CTE several times, or maybe you use some other queries, false queries, this object can have several consumers in the tree, and the resources that you associated with this node can actually be allocated by this tree not only upwards in a cascade way, but also in terms of a graph. So this is a graph where the threads of data and resources go towards the field. So let's think about these strange things that you can notice, or the ones that we encountered when doing this service. First of all, this is the fairy tale of the lost time. If in your life you have ever faced on even number arithmetics and its implementation in computers, you will understand that if we take some rounded, and the time is rounded up to milliseconds, we take this rounded time and we multiply it by something, and as I said, we have to multiply it by the number of repeats in the node. So if this number is several thousand, several hundreds of thousands, the arrow for rounding can be in milliseconds or even in seconds, because if Postgres is used, for example, as an elapsed system, then the number of these cycles can be really high. It can be up to 1 million. So this is a very simple example of a mistake. If you extract one number from 1 and you think that you get a different number, well, it's not always true. If you multiply the second result by a major constant, you will have some abnormality and you will have to deal with it in future. And these abnormalities are accumulated when you multiply and when you sum up. Multiplication. In case of multiplication, it happens because this cycle in the node is repeated several times, and during every loop we can get an arrow of 1/2 of microsecond. If there are a lot of nodes, the range is really high. And in terms of the tree hierarchy, we see the summarization of these arrows. For example, in the plan you can see that there are two daughter nodes that took 1 millisecond. Then the parent node will take probably 1 microsecond or probably 3 microseconds. You know, this is 3 time difference. That is quite significant. Okay, let's discuss the second problem. How can we allocate the resources in a plan? This is a problem of subqueries. Normally, they are represented in such nodes as initplan and subplan. Initplan writes that it returns something upwards. In your query, you write it is equal to select something and you get initplan. For example, here, $0. This is the result of this plan, and somewhere above it, probably not its ancestor, probably it's somewhere it's located on top of the tree, probably it's located on the side of the tree. There is a consumer in whose filter, in the conditions of this index, this box 0 is recorded. So the correct plan is actually it is correct towards the consumer, not towards the ancestor. But in some cases, initplan gives several such results. For example, when you provide a record as a result, so an integral record that has 2 or 3 fields, and the matter is that each of the fields of this record can have consumers on the tree that are located randomly. And actually in this example, we're quite lucky that one key became index key and the other one was used for filtration. It's not always like that. So the situation can actually be divided into several nodes. This is an example that we can have with 3 keys in one subquery. Now, let's speak about resource cloning. If we look at the row texture of a plan, we can see that part of the data, that is row about time and the number of read pages, can be encountered twice in the tree. For example, if we read something for common table expression and after that we read it from common table expression, then we can see these resources and this time twice. But actually, these data were read only once, only when we extracted them from the table. It's not a really difficult query with this kind of plan. It is this kind of query. It's very easy to get it. So we allegedly ordered generation of CTE from the whole body of PG table. So if you saw this table, you know that normally it contains several hundreds and thousands records. And in the first false query, up to 1 million, we requested 1 record, and the base is smart. It did not read several thousands records. It read only 1 record, 1 page of the data that we required. And after that, we asked it to read the record 101 in addition to the record number 1. So the base read 2 more pages of data from the table. It read 3 pages of data, and we represent them here on the right. Although, judging by this sum in the tree, the result is 6. So, when we allocate the resources in the tree, we actually prepared the flow chart. This is the diagram of threads, regarding the way these data are allocated. Normally in our life, this situation is more complicated. It looks like that. For example, from 1 STE, it is extracted 5 times. I'm not sure that this query is really good, that we had to read it 5 times, but sometimes it happens. So the next point is related to common table expression. the, the written ones. These are the ones inside of which some node is present. If we just look at the figures generated by the plan, we will see that inside CT inset there are 30 pages of data that were used inside. I won't speak about wrapping now. After that, we read it from the CTE, and we can read only 3 pages, but where are the remaining 27 pages? It's not clear. But actually, if we look at the query that generates this plan, it will be quite clear. Inside CTE, we generated 10 records physically, and we returned all of them. But after that, there is a problem. The consumer that is outside didn't want to have these 10 records. They wanted only 1 record. They read it, but where are the remaining 9 of them? This is not magic. They were to be allocated somewhere. So, to avoid such abnormalities, for these resources not to lag somewhere, we realized that actually when we prepare a diagram, there are 3 cases. The first one is when CTE is a written one and no one reads anything from it. So during the query, you made an update, you updated this record on the basis of new information, and you didn't do return. In this case, the resources are just added into the total amount of final results of the plan. The second option is that when you made a return and you read everything that was returned, for example, the whole single record. If you read the single record, you will get the plan where this is not a root, where this is just an intermediary node in the diagram. And the third option is the option that I described before. So it seemed to us that we had actually read something from this node, but we didn't read anything. And where can we put the things that we hadn't read? At first, we were not able to show it correctly, but after that we decided that still we need to allocate it to a pseudo root. And if we can see this pseudo node, then the total amount in terms of the planned resource at the time of its execution and the amount of consumed resources becomes similar, and there will be no abnormalities and negative values. And we showed this node on the diagram, so that's it, the logic is closed, and that is really beautiful. Another issue, parallel nodes. When the infrastructure of parallelization of nodes was introduced into 9.6, the following abnormality was present. If you can see in the plan, parallel nodes, parallel together, you can get the problem of visualization. And unfortunately, up to version 12, when the plan represented detailed statistics for every worker, it wasn't possible to do anything. So what does it look like? You completely scan the log of the base, and you can see that actually in case of parallel execution of query, if auto-analyze module is on, you will see 2 plans. The first one is the plan with main process, that is the leading process in execution of this query, and a part of it that starts from partial flash aggregate, for example, and it comes to us from daughter process, from worker process. So this is worker process and the node. And looking at this example, we can see that actually worker, 500 buffers, 500 pages of data were read by the worker. So the node in master process read 1,500 buffers. And we give it upwards to gather. In gather nodes, we see 2,000. That is good. And when we got one step upwards, we see 1,500 once again. This 1,500 were in master process only. Why? This is an abnormality in all versions. And in new versions, we actually hope to have it improved, and we will see the situation adequately in terms of workers. But unfortunately, when we have only the plan of master process that normally when explain analyze is executed, you will get from console this information and you cannot do anything about this data. And when we parsed it, we realized that actually, when we draw a plan, we notice some typical issues. And maybe some long time ago you played this game, and there were such advisors that gave you tips in some situations. They said, it's better to do it this way. Right now, do it this way.
Такую же роль
So we assumed this role and thought, why would we give tips orally to our developers? Let's make a system that will generate tips automatically. And we created the so-called structural tips. A classic example would be a developer comes to you saying, I'm writing a query, please provide the recent 10 documents on this and that. And he's saying the plan is really slow. And we see that in the plan there is an index in the key, and the title of the document is Vasya. Then the sorting under the date which the developer forgot to introduce into the query. So he read 1,000 records, sorted them out, and cut the last 10 for its paging. Why do this in such a complicated manner? We understand that if we add to our index this date field as the second key, the second query, without rewriting it, will provide us the sorting plan, and we will have those recent 10 with the date sorting. So we started collecting the basis of such standard patterns, which we understand where they come from. The first and the most frequent case is bitmap end, bit operations. It cannot always be resolved, but in most cases they are errors, unless it was not intended coding by the developer. So you see the bitmap end by the first index and the second index. This means that in the query the developer said VA equal 1, VB equals 2. And there is a separate index for A and a separate index for B. The basis can understand it even in this case, but if you can, as the DBA, create this index, do it with two sets of fields, A and B, a compound one. Maybe you will develop some custom statistics to make it even more effective and efficient. So the same query, without being rewritten, will still be efficient. These are all trivial conditions as we scan indexes without ranges, but they generate the major part of the problem. Another situation, the same query A equals 1, B equals 2, and we have indexes for A and B. So far, up until version 12, the query planner has not been able to resolve such cases more effectively. I'm looking forward to the day when it happens. So the developer hasn't learned how to do this. The simplest way is to look at how your index conditions overlap, if they overlap at all. And this will be an alternative. This field is not null, so the conditions do not overlap. Separate extraction of data from those tables and glue them through union, depending on whether your queries can overlap in terms of data or not. The next option or case. So we read, and read. We read so much from the table that 80% had to be taken away, thrown away. 80% of all the records had to be thrown away from that node. So rows 10 or 20, rows removed 80. Why did you read so much? Even by index you read so much. Do not read so much in the index. Or maybe you missed the index that was more focused in your plan, or you need a more specialized index. Pick the existing one if it is necessary for this query and provide parameters according to the conditions. You can address it in the same manner if you read the index and you haven't finished reading. You either need the second index or you need to modify this current index. Under sorting. This is what I started with. Very commonplace. Sorting fields, include them in the index and you'll be happy. And maybe it will take up slightly more resources, but it will not take up too many resources for this specific query. This is my advice to you. Another case. For instance, we take a table, some queues, and we started updating the same records. Update, insert. There were not too many records, maybe even one, but there were too many operations. Thank you to the multi-version, we get a lot of copies inside our table. The vacuum can reach or not reach it. If it doesn't reach it, the only records from this table will become very expensive. And we see that happening if the number of read records or thrown records is small and the number of consumed resources is high, by several pages per record. That means you need to launch vacuum on that page and better vacuum full if you can afford it. If you use CTE in your query in an active manner, reading from CTE is not an expensive operation. It may be more expensive and time-consuming than any other operations. If in your query you have two big CTEs, you are lucky if it is done through JSON. But if your query looks like nested look, and by the second CTE you have multiple repetitions, CTE with a lot of loops, this will be very expensive. The solution is to use various versions of materialization of the CTE into a type which support addressing through a key. Instead of doing join with filtration and selection of a lot of records from CTE, you will make one operation with a specific key. So these types are HStore, JSON. I wrote an article about it recently. You can check it out. And the final case, something went wrong. So we read from the memory very few pages and we returned one or two records, but it took us 1.5 seconds or more than 100 milliseconds, which is not normal. This means that you either faced blockage or locks, and that means you cannot do anything here. Read the record or insert the record, or the second option is you faced a shortage of resources allocated for your computer, or the Hyper-V in your virtual machine did not provide resources. This is bad, so you are facing processor shortages. That means go and check what has been happening on the Hyper-V. Let's go back to more beautiful things. let's color things. We will color. We will not color the plan. The plan is already beautiful. We will color the query. This is an unformatted query, especially when the developers glued together the body of the query. It is not good. Let us draw it in a more beautiful way. If we can draw beautifully, reassemble the body of the query, then we will be able to stick a tip to each query, explaining what was happening. So for that, first we need to understand the query, because our system works on Nodal.js. Do the following. These are the extended bindings in the internal area of Postgres, compilated grammar. So we took foreign modules as a basis. So we feed the body of the query and receive the disassembled syntactic tree as a JSON object. Then you can walk backwards across this tree with formatting. We thought it would be a good idea. When we disassemble it and draw the way we like it, the developer will want to have it as beautifully, to have it and inserted in his code in this beautiful way. You have three ways to how to do copy-paste. The first option is as is, so we reformatted the query and it can be copy-pasted. You insert it into the application code. If in your query you have parameters, and those parameters have been extracted from the query, and you want those parameters to be inserted somewhere, so you're too lazy doing this by hand, so we can add the values of those parameters in the structure of the query. This is good. And then you'll be able to see what will happen. This situation is not always possible, not always good, because in some cases, in the versions up to 11, those versions do not know how to send parameter values into the section keys. So if you wrote the values of the section key for 10 as a transferred parameter, you will have issues. But you will not see those issues immediately. Those values will be translated into the appropriate mechanism, but to understand the problem, you will need this prepared statement. And option number 3 is simple copying. But how is it possible to take the plan which we discussed on step 1 and the query which we discussed on step 2? Let's take a simple example. We have a query which generates one CTE and calculates 2 times, exactly the same that we had in the middle of the presentation. It generates the following plan. If you look at it attentively and remember that up to version 12, CTE generation was an absolute barrier for the planner, for the scheduler. So if we see CTE generation in some query and generation of CTE in the schedule, then there will be a clash. So a task with an asterisk. CTE can be single name inserted inside CTE A. You can create CTE X And at the same level of city B, you can create city X. As you compare, you should understand this. Understanding this with your eyes, even when you see the schedule and the body of the query, is not easy. If city generation is complex, inserted, and the queries are long, you will not be able to realize and see all this. If in the query we have union node, then there will be append node corresponding to it or some recursive union. What is on top of the union, the query, is node 1 of our schedule. So the first child with respect to the parent node. If through the union we have several units, select one union, select two union, select three union, then there will be one node but with several children, not just one. When we partitioned it, we can draw it beautifully and show for this union node that this is the node that we need. Now the assignment with an asterisk. Inside the recursive selection generation, you may have more than one union. Surprise, surprise. But always, only the last unit is recursive, coming right after the last union. This is, in fact, union 1, not recursive. This is the generation of the start selection. So you should know how to unglue it. So, for instance, we had 3 of them, and the recursive unions corresponding to them. So now that we know the query structure, and we know which bit of the query corresponds to the bit of the schedule, and we can get the readable objects to those units. We do not know whether it's in the tables or CTE. We simply see that something can be read. Something can be read is a limited number of nodes, index scan, CTE scan. We know the structure, we know the blocks, so we do this assignment with an asterisk. So we take the query, we read 2 times from CTE, check the schedule, and see a problem. Why do we have the alias with a number? How did we get it? So Postgres adds it on itself, by itself. So, but it doesn't make sense to us. It is simply added here, so we won't pay attention to it. The second assignment with an asterisk. What if we read from the section table? We will get append or merge append node made of a great number of children. Each of them will be a scan from the section plan, or an index scan, or a text scan. It will not be a query. In any case, we understand these nodes, we get them together and say everything that you've read from the mega table is here and all the way down the tree. Simple cases. Values by values result from query without from, or something that turns into one-time filter from the schedule point of view, when you have a false expression in the unit. You write something, and then all false. So 1 becomes a parameter. You'll get a one-time filter, and the result a node in the schedule. Function scan. These are SRF functions. As to inserted queries, it gets more complex. They do not always get into the plan, into the schedule. Sometimes they turn into join or anti-join. You write not exist, and it turns into anti-joint for some reason. So it is hard to align all this. There are no corresponding nodes. Another assignment with an asterisk. So everything looks good, but if you have several values in the query, you will get several values in the plan. To differentiate one from the other, you'll get values, values underscored, and values 1. So Postgres adds those indexes as it finds values in the units as it goes through the query from top to bottom.
So we discussed everything, and what else do we have? That is limit. Well, it's quite clear that limit of the node is quite simple. Simple nodes are mapped in a similar way. No magic here, it's not difficult at all. But it's difficult when we want to join them. However, sometimes we can do it. In terms of parser plan, we have a node join exp that has the left and the right descendant. This is something above your join and below your join in the query. And in terms of the plan, these are two descendants of a loop or a joined node. So that is loop hash anti-join, something like that, and it has two descendants. Join node always has two descendants. So let's use very simple logic. If we have AB tables that are joined in the query, they can be located in the order of AB or BA. We can try combining them till we run out of these pairs. So let's take the tree, let's take the plan, and let's redraw them as graphs. Now it is more clear. And let's take into account that we have join node that has B and C children. Actually, the order is not important for us. These are the children of join. Let's combine them. And look at it once again. It turned out that we have the join of A node and B and C pair on the one hand and on the other hand. Let's join them. That's great. Here we connected two joins. As a result, we managed to draw a tip for join and specify, well, this is head join, and in the query you had normal join, and this is the amount of time that you spent on it. And once again, this is a task with an asterisk. Unfortunately, we cannot always solve this task. And when isn't it possible to solve it? You write A join, B join, C in the query, and everything is fine. And after that, you draw the plan, and you can see that the distant nodes were interconnected. These are A and C nodes. But actually in the query we do not have it. They are not close to each other. There is no tip here. And irrespective of the way you place them, nothing will help. The same is true about the comma when you write A, comma, B, comma, C. Unfortunately, nothing will help you. But in most cases, we can untangle almost all joins, and we will get this kind of query profiler in Google Chrome. So you can see the amount of time that was spent for every node. And for you to use all of this in an easier manner, we started storing an archive. And in the beginning of December, our service was launched, and we added 3,000 to 4,000 of them. You are already using that. And you can send this link to your colleague, and after that, you will check it. If you don't want your plan to be in the archive, you can remove the tick and state that you do not want to have it published. That's it. Thank you. Kirill, thanks a lot for your brilliant presentation, but unfortunately, we do not have any time for questions, so we can have time for 2 questions maybe. And other questions will be asked during Q&A session. Hello, thank you for your presentation. I have the following question about the evaluation. So you described in the very beginning the evaluation of time of query plan. Unfortunately, sometimes we encounter queries that cannot count, explain, analyze in their original form. It becomes slow. What do you mean it cannot calculate it? Well, it is not executed, so it takes so much time, yes. 24 hours or even more. These kind of queries. So, we have to be guided by a simple explain. And due to its specific features, there is an error there. And is there any way to get a more realistic evaluation from simple explain? More realistic than it was programmed by the developers? Unfortunately, no. So the way it shows it to you actually is appropriate for the nodes. So from the standpoint of the nodes, it will be like that, but the amount of money and resources that you spend for the execution of every node will be learned when you execute it. Unfortunately, the statistics of execution is available only in the end of query. We have another question. Thank you for your interesting presentation. How do you settle the issues with Vue and SQL functions that sometimes can get into the plan? If this SQL function was deployed in place, unfortunately, in terms of the query, we have no information on its content. We do not go into base, so we just can see something that is present in the logs. So that's it for us. We cannot do it. And regarding Vukes, it's similar, yes. If it was deployed in some query, unfortunately, it won't help. And if it is not tangible, it is always deployed, yes. If it is tangible, well, if it is not tangible, well, sorry, it didn't manage to do that. Okay, one more question. Do we have another question? Okay, then all the questions will be asked during the session devoted to conversation with speakers.